Recording in progress.
All right, welcome back, everyone. We finished chapter 3 a couple days ago. We'll do chapter 4 at the end of this stuff, right before the midterm. It won't be on the midterm. It's stuff we'll use for chapters 8 through 13. But we will have 1 through 7, except for 4 on midterm. Today we're doing chapters 5. We're going to do about half of chapter 5. We're going to do 5.1 through 5.3. And chapter 5 is on probability. Okay, so probability, just for a quick definition for you, it's the long-term proportion in which a certain outcome is likely to occur. Or is observed. If we see the outcome, it's one of the things. And it's got to be in situations where there's short-term uncertainty. And I'll give you a second to write that down. I'm going to make a little die tracker real quick. Okay, so I got a couple dice. I'm going to roll them. I'm not going to add up the values. I'm just going to record them. So I got a 3 and a 2. And so you might think that we got a strong chance of rolling a 2 or a 3. I roll again. Look, we got another 2 and I got a 6. And ooh, I got another 6 and I got a 5. I didn't get a 2 this time. Oh, I got 2 6s. Well, these are good dice. I like these dice. 2 and 3. So when I say short-term uncertainty, I don't know what I'm going to get when I roll these. I didn't know I was going to get a 4 or a 3 this round. But if I do this enough times, and I add them up and do like a histogram for them, the bars are going to be pretty close to the same height. And if I could do it an infinite number of times, they would be the exact same height. There are 6 sides on a die. And the odds of any given side coming up are related to how many total sides there are. So total is 6. And whatever number I'm looking for, like x equals, say, 5, how many outcomes are on the die? There is only one outcome on each die that has a 5, so the probability would be 1 in 6. Okay? That's the long-term probability, or this is the probability, or long-term proportion. The short-term uncertainty is I just don't know what I'm going to get when I roll. Okay. Something that has the same probability for every single side or every single event. Is it called a uniform distribution? When every outcome is equally likely? Or equally probable? So in the short term, we don't know what we're going to get. Even if we do it 100 times, it's not going to be balanced. But as maybe I should wait and give you a sec to write all this out. If you need it up longer, give me a holler. Say something. Okay, I'm going to erase this part right here in case you're still writing stuff below. So if I track how many times I throw the dice, let's say it's n times. I throw the dice n times. For small values of n, when n is low, the results don't reflect the long-term stuff. The probability. And we saw that with the dice that I rolled. I had like 4 6s. I had 4 3s. I didn't roll a single one. And yet we know a 1 is going to come out up about as equally probable. So when we have a low number of tosses, we're not really getting a good probability if we look at the results. However, as n gets really large, the experimental results, and that's what I was doing. I was doing an experiment, rolling the dice. The experimental results will approach the true probability. And this idea is called the law of large numbers. And I can give you an example. Let's say Let's say I'm flipping a coin, heads or tails. Coin flip, heads or tails. And I have done it, 500,000 times. This is unrealistic, but I've done it 500,000 times. And I have 249,985 for heads, and for tails I have 251, 15. The experimental results I can do in a calculator. I can see what the percentage chance is for either one. 249,985 divided by the 500,000. And I get 0.49997. So I get 3 9s and a 7. And if I do the 250, that should be 250, 15. That doesn't add up to 500,000 the way I had it. 250, 15 divided by 500,000 gets me 0.50003. Okay, so what I mean by law of large numbers is, let's say I throw the dice 5 more times and all 5 of them are tails. Okay, so 5 more tails plus 5 tails. That's going to raise my tail count to 250,020, and my total coin flips to 500,005. And when I do that, let's see what happens with the probability. I've got 250,020 divided by 500,005. And I get to the decimal places I have already 0.50003 to 5 decimal places. Rolling 5, flipping the coin and getting 5 tails in a row, which is not easy to do, did not change the probability at all. So that's the idea of large numbers. Eventually, you do it enough times that doing it more times doesn't change the outcome. I use 500,000 so I could show it to a lot of decimal places. Normally, we're not concerned with 5 decimal places like I have here. But the idea is the same. If you do it enough, the true value comes in. I might have gotten 5 tails in a row in the beginning, and it might have been 0 heads and 5 tails. So you have to do it a lot. You can't just do it 10 times. You can't do it 100 times. You got to do it a lot. That's the idea of law of large numbers. And I'll give you a couple seconds to process that. Anyone need that up longer? Okay. Real quickly, what these look like, these values that we've done with proportions right here, this is the frequency, and this is the relative frequency. So I suppose if you recorded every event in StatCrunch, you could use StatCrunch to compute the probabilities. And there are areas that we will use it for some of it, but most of this is going to be calculator work. Okay. Some more terminology. The sample space usually goes by S, is the set of all outcomes, possible outcomes. So for the die roll, we had 1, 2, 3, 4, 5, and 6. That is the sample space. They often include it in curly braces. And for the coin flip, it was heads or tails. Now that's the sample space. So this is the sample space for die rolls. This is the S. This is for coin flips. They call an event and they usually use E for it, or EI, is a collection of one or more outcomes. And you don't have to list every single outcome. It could just be you were looking on the die roll for rolling a 6. You may only care about the probability, or E being roll a 6. Or it could be E is roll an even number or an odd number. Maybe I'll use different letters for now. Or I could just say I could do 1 or 6. Like maybe I want the highest or lowest number. Roll a 1 or a 6. So it can be whatever you want to call it. So these are a list of like events. It's not a complete list of possible events for dice rolls, but it's just some sample or examples. Whoop. So when we talk about the probability of an event, we use P. We will say the probability of event E we write it like this. We do P parentheses E. So there's, or another possible way of writing this for rolling a 6, or we could put, or P that X equals 6. X is usually listed as an event as well, in an event. So you'll see that a lot. Since roll a 6 is the event E, these two kind of mean the same thing. And what they mean is to list the total number of outcomes that are in the event. In rolling a 6, there is only one outcome of a 6 out of 6 total outcomes. The probability of doing F I could write it also as probability that x equals 1, 3, or 5. Well, there's 3 outcomes in that group out of 6 total outcomes. And you could simplify that or reduce it to 1/2. As a reminder of how to do it, we could write 6 as 3 times 2. And when you can't see a number on top and bottom of a fraction where there's no addition or subtraction in there, just top and bottom, you can cancel them out and leave them a 1. So I've got 1 on top and 1 times 2 on bottom. And so if I were to do probability of rolling or probability of G, or probability that x equals 1 or 6, how many outcomes do I have there?
Wouldn't you have to add 1/6 plus 1/2?
What do you mean?
Because you're saying P of G is when the probability of X is equal to 1 or 6.
The
So
rolling a 1 or a 6, either roll. How many possible events does that add up to? Don't, if you're trying to do the probability rules, we'll go over those in a second. This is there's another way of doing this, just how many outcomes are listed. 2 outcomes are listed out of 6 total outcomes. Like 1 is an outcome and 6 is an outcome, so there's 2. And this simplifies down to 1/3. There are rules where that has an or in there, and we'll get to that. And now I'm wishing I hadn't wrote x equals 1 or x equals 6. I was trying to be more descriptive, and I think I threw off some stuff. Do you guys need that up longer? Does anyone need it longer? Okay. So some rules with probability. I don't like that. So what do I gotta do? There we go. So probability rules. First rule. The probability of any event is always greater than or equal to 0 and always less than or equal to 1. 0 means it never, if it equals 0, it cannot happen. And if it equals 1 exactly, it's the only outcome. This is probability is like a decimal version of a percentage. So a probability equal to 1, that's 1.00. If I write it as a percentage, I move the decimal right twice and I get 100. if it equals 1, there is a 100% chance the event will happen, which means there's no other possible outcome. And if all of the events are unique, the sum of the probabilities has to equal 1, which means all the percentages add up to 100%. In terms of the dice rolls, I could do probability of rolling a 1, probability of rolling a 2. Maybe I should use the x's while I'm still starting this. The probability that x equals a 3, the probability that x equals a 4, the probability that x equals a 5, and the probability that x equals a 6. Each is 1/6. And 1/6 is 0.166. It keeps going. So we have this going down the row. And when this bar means the 6 keeps repeating, so that just means it's like this with unending 6s. Eventually we would have to round somewhere. The rounding can throw off the adding up. If we add these all up, it should equal 1. When we do the rounding, it might end up being 1.01 from rounding, but it's always close to that 1. Not the most exciting stuff going off over all the definitions and stuff, but we need it to get somewhere. And probability is, this really plays or proportion really plays a big event for the rest of the semester. Do you guys need that up longer? If you do, holler. I'll bring it back. So I had said probability of an event is the, really when we do it in an experiment, it's the frequency of event E over the total in the sample space. One way of they like to write it is they say n of E over n of S. N is for number here. Number of events E over number of events in the space, or number of possible events. So you see the N, E, the NS, they're really just talking about the number that's done. So rather than giving a percentage, just how often you flip the heads. So I had 249,985 for my coin flips. That would be the N of E here. Something students get confused. How is relative frequency different than probability? Because they look and act the same. They're calculated the same way. It's the exact same way you calculate them. The difference is it's a matter of when. Okay? Relative frequency it measures how often an event occurred during a specified amount of time or number of events. It's something that's happened in the past. Probability is the likelihood of a specific event happening in the future. And when it's something like dice or cards or something like that, this is called the classical method. The classical method is when, or classical probability is when outcomes are equally likely. Outcomes, not events. When outcomes would be like a 1, a 2, a 3, a 4, a 5, a 6. One given outcome. When I did the probability of rolling an odd, my event had more than one outcome in it. And so you'll see these a lot in casino games.
Could you give an example of a classical method? Because I'm kind of not understanding it.
Yes. Let me make. I was going to actually do that with the deck of cards. But I want to make sure everyone's got this written down before I jack the space. Anyone need this up longer? Okay. This is right here. So in a deck of cards, there are 4 suits. These are the diamonds. These are the hearts. Then the shape looks just like what they say. The one that looks like a heart with like an arrowhead kind of thing is called a spade. And the one that looks like a clover is called a club. And within each suit, there are 13 cards. They range from ace, king, queen, jack. Those are the number or cards without a number on them. And then the numbers range from 10 to 2. Each suit has this. Ace sometimes counts as, the A is for ace. It sometimes counts as a 1. Notice the number of symbols in the middle. And any other given card shows the symbol in the middle other than the face cards. So like this is the 6 of clubs. There are 6 clubs in the middle. There are also, I'm telling you this because there are questions about cards in the homework. And if you've never seen a deck of cards, this might be unfamiliar to you. There are 3 face cards. They call them face cards because they have faces. K is for king, Q is for queen, and J is for jack. I have no idea why they have a jack. I don't know why they don't have a prince, but they have J for jack. Maybe it's prince of all or jack of all trades. I'm not sure. So each suit has the ace through 10, which is 10 cards, and then jack, queen, king makes 13. So each suit has 13 cards. There are 4 suits. Write this down. Four suits, that's what they're called. Diamonds, hearts, spades, and clubs. Everyone knows the names of the diamonds and hearts because we have them in our Lucky Charms. Those are the names of the other 2. These 2 are red. The diamonds and the hearts are red. The spades and the clubs are black. Each suit has 13, they're called ranks. One through 10, jack, queen, king. And the 1 is called the ace. And then we've got jack, queen, and king. So there's 4 suits, 13 ranks. That makes 4 times 13 is 52 unique cards. So when I say classical outcome, the probability of drawing a 2 of diamonds is the same as drawing the probability as drawing the king of spades. Same as probably as anything else, there is 1 card of that nature over 52 in the deck. So equally likely outcomes. And if you've never used a deck of cards or are completely unfamiliar with it, you can always Google the words deck of cards, click on images, and they will give you a picture. There are millions of pictures of decks of cards on the internet. So you don't need to buy a deck of cards. You can look up the image any given time you want. There's none that I would recommend over any other. They all kind of do the same thing. That's the classical method. There's another method called the empirical method or experimental method. And when you guys are done writing this, I will show you.
So the classical method, like it's just like that, like the 4 times 13, or like what's the classical method? Like what do
Is
you
the 1 over 52 equally likely outcomes? I was just using the 4 times
Oh,
13
okay.
to show how many cards there are in a deck of cards.
Oh, okay.
Okay. For dice, when you're rolling a die, it's 1 over 6. For a coin flip, it's 1 over 2, heads or tails. There's only 2 options and they're equally likely. We're assuming the coin doesn't land on its side. I guess that's technically possible. But we don't, it's kind of hard to calculate the probability of. We would have to flip a coin millions and millions and millions of times, maybe to get it to happen once. So it's so unlikely that it doesn't really affect the probability. If you need this up longer, let me know. I'm going to talk about the empirical method now.
Wait, can you go back to that page?
Yep.
Can you label those two, the roll a die and the coin flip? Like which ones? Like
What do you mean?
you said that the roll a die was what?
1/6.
Oh,
1
okay.
over 6.
Oh, and that's part of a classical?
Yeah, because
Oh,
there are
okay.
6 different sides to these dice,
Oh,
and
okay.
each outcome is unless the dice are weighted.
Oh,
There
okay.
are people have made cheater dice where one side's heavier and so that side lands on the bottom more.
Yeah.
But in regular dice, they're equally likely.
Oh, okay, okay. I thought those were like a different method, like an
No.
empirical or whatever. Oh, okay. Okay. Awesome. Thank you.
Uh-huh. Okay, so real quick, we will just do deck of cards before I go on to the next one. Images. Pick your poison. I mean, there's some good ones here. This will show you all the cards so you can work with them. And you know what? I might leave this up on this because I might use it in a second. The other thing I want to do is show you the empirical method, and the easiest way to do this is look up the game Past the Pigs. Past the Pigs. Oh, I don't want the image. Go back. They're cute little pigs. Where's the Wikipedia? There's the Wikipedia. So there's 2 pigs. One side of the pig has a dot. The other side of the pig does not have a dot. There are 6 ways that the pig can land. And they are listed below. So the ways they can land, and I'm going to write these down. I'm writing down this chart right here. Okay. So the options are side with dot or side without dot. That's the first one listed. Side with dot. A razorback is when it lands on its back. Side without dot means when you roll it, the pig lands with the dot free side up, facing up. Razorback is the pig landing on its back. A trotter is when the pig lands on its feet. So you kind of toss them like dice. Snouter is when it lands on its front 2 feet and is leading on its nose, its snout. And a leaning jowler is it's leaning on 1 foot, its nose, and its ear. It's a really awkward way for the pig to land. If we were doing it in class, I have pigs in my desk drawer. We would use them to do this. So the percentages listed are, and I'm going to write them not as percentages, but as decimals. I'm writing those decimals real quick. Okay, so this is past the pigs. Oh, one more thing I got to grab from there. The number of times they rolled the pigs to find it. They tell us they calculated this using a single pig, using a standardized surface, which I assume is just a flat surface, and a trapdoor rolling device, maybe so they put the pig on the top, and then you let it go and it rolls through a bunch of things before it lands. That way it's not like some individual could make it land one way more often than another. It says they rolled it 11,954 times. So I'm going to write that down real quick. So these are my probabilities, and this is the number of times they rolled the pigs. This is called the empirical method. This black pen is dying. I need a new one. Or another word for it is experimental method. Now, one way to find out if they did this enough times is the following. I can take this 11,954 and multiply it by the frequencies and figure out how often they rolled these things. So, for example, I am going to do 11,954 and multiply by 0.349. And I'm going to get 4,000, if I round to the whole number, 4,172. And I could do this for all of them. But I'll just do it for the top one and the bottom one. Times 0.0061. This is another example of how we can show the law of large numbers. So they did this 11,954 times. If they rolled it and they only got 73 leaning jowlers, it doesn't happen very often. Let's say they rolled it one more time. And this goes up, n goes up to 11,955. And the leaning jowlers go up to 74. We can calculate the leaning jowlers probability again by doing 74 over the 11,955. the probability that X equals a leaning Jowler, I'll use LJ, is 77 over 11,955. And in a calculator, not 77, 74. I am getting 0.00618. I guess it's going up to 62. Which means the percentage chance went from 0.061%. Nope, 0.61%. Which is not very often, up to 0.62%. Still not very often. That's the idea of law of large numbers. If we do it enough times, doing it another time doesn't really change the probabilities much. So you'll see doing stuff like this where I calculated how many times were rolled. You'll see stuff like that in the homework. You might see something like the probability of being left-handed is, I don't know, let's say 0.11. How many, if we have 5,000 people, how many can we expect to be left-handed? And what you're going to do is the same thing I did here. Up above, I took the probability and multiplied it by the number of people. 0.11 times 5,000 is 550. And this is not an exact value. It's approximately 550. So we might have 548. We might have 537. We might have 559. But it'll be somewhere near 550. Okay? They'll ask you for stuff like that. Five 5.1 is the longer section of the three we're doing today. Hopefully I can get all three done. Well, yeah, one or two more things I want to say in this section, and it should be really quick. Does anyone need this up longer? Okay. Back to the deck of cards. If you have not used the deck of cards, so if they ask you for the probability of drawing in any given card, I'm off screen. Any one card, like say Ace of Spades, it's 1 over 52. If they ask you the probability of picking a specific suit, like suit equals hearts, there are 4 different suits. Only one of them is hearts. It's 1 out of 4. This also relates to total number of heart cards in the deck. There are 13 cards of each suit out of 52. So we could do it by the number of cards. 13 cards out of 52 have hearts, or we could do it by suits. There is 1 suit out of 4 suits that have hearts. They might ask you the probability of red or black. probability of a specific color for a deck of cards. There's only two colors, red and black, and they're each equally likely, so it's 1/2. That's because there's 13 hearts, 13 diamonds, 13 spades, 13 clubs. Each category has 26 cards in it. 26 over 52. So again, we can take it back to the individual number of outcomes and add those up. If you like poker, and you may not now, but you might one day, Texas Hold'em, you get 2 cards face down. And the probability, and these are called your pocket cards. This is Texas Hold'em, not like 5-card draw. They're called the pocket cards. The probability of getting a pocket pair or 2 of a kind in the whole cards is 0.0588. This is some fun stuff, which is 5.88%. If you want a particular pocket pair, like pocket aces, which means your 2 cards face down are aces, also called pocket rockets because the aces look like rockets, the head of a rocket. This is 0.00452 or 0.452%. So they will, when they ask you if something is unlikely, unlikely outcomes, unlikely events or outcomes occur less than 5% of the time. Which is 0.05. So another way of writing it is the probability of the event is less than, I guess it could be less than or equal to, 5%. And one last mention for 5.1, subjective probability. Is based on personal judgment. Weathermen do this, or they used to. Economists. People that look at what happened in the past and they just say, I think it's going to be a bull market, or I think it's going to be a bear market. They have no idea. There's no way of figuring it out experimentally other than just waiting to see what happens. So they are using their personal experience and making a judgment call. Five 5.1 is the longest section of these, I think. 5.2 is a little bit longer than 5.3. I think we can still get it done in an hour. The hour left. This is one of those long day events. 5.1 usually takes the longest. 5.2 and 5.3 are so related that I hate teaching them on different days. If you need this up longer, let me know. Otherwise, I'm going to go on to 5.2. Okay, 5.2. 5.2 is called the addition rule. And we also talk about something called compliments. And it's not like, hey, you look nice or something like that. I like your dress. I like your, tie. Compliments with an E right here. So, has everybody played the game Monopoly? I hope you have. I'm going to use a Monopoly example from Monopoly, game of Monopoly. There's a square on Monopoly called free parking. And when there is a lot of hotels all along the street, that's one of the only safe spots to land. Some places, some families have a house rule where all of your fees get, like all your dues and stuff, all the money gets put underneath it, and it's like a jackpot prize when you land on it. If you land on free parking, you get the prize. It's not part of the basic rules, but it's an example. Let's say you are exactly 8 squares from free parking. I think that's Waterworks. God, I hope it is. And so, what are the ways that we can get? So you want 2 outcomes. You either want either A, to roll an 8, or B, you want to roll doubles. Because you either get to go again, some cases you want to go again, get around the board faster, or if there's enough hotels, you really want to just go to jail, so you're stuck in jail for 3 rounds. And you don't have to risk landing on a hotel. So, what are the ways that I can roll an 8 or doubles with 2 dice? Well, if one of them is a 1, I can't do anything with it. The only one that matters would be let's look at the 8s first. So the 8s. I could roll, I can't roll a 1 and a 7 because there's no 7s. I could roll a 2 and a 6. And I think I want to use a different colored die for this, because this kind of matters. Use red and black. So I could roll a 2 and a 6. I could roll a 3 and a 5. I could roll 4 and 4. So, like, let's say 3 and 5. That's one way I can roll a 3 and a 5. I could also get it where the red die is a 5 and the black die is a 3. We have to count those as separate ways. So I'll say 5, 3. And finally, I could do 6, 2. Wow, this pin is dead. And now let's take a look at the ways we could roll doubles. I'll abbreviate it DBO. I need them to match. So doubles would be 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So how many ways are there to roll an 8? There is 1, 2, 3, 4, 5. There are, for doubles, 1, 2, 3, 4, 5, 6. But notice I have 4 and 4 on the up there twice. I can't count it twice. So I'm going to say I'll call this the overlap category. Overlap is the 4 of 4. There is only one event that has an overlap. So if I say this is where the ors come in. If I say the probability of rolling an 8 or double, I could either add up the total number of events that happen. Of these, there is 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to count the 4 or 4 because I already counted it up here. 8, 9, 10. So 10 outcomes. There are 10 outcomes. There are 36 ways to roll dice, or roll 2 dice. And it comes from 6 times 6. The outcomes on each dice. There's 6 outcomes on each dice. We get 36. Another way to do this, using the information we have right here, I could say the probability of rolling 8 or doubles equals the probability of rolling an 8 plus the probability of rolling doubles minus the probability that something is an 8 and a double. Maybe I'll try to put this on one line. I'd rather have it on one line. Mine's probably that's 8 and double. There we go. And let's look at the events we have up here. The probability of rolling an 8, there's 5 events out of a total of 36. The probability of rolling doubles, there is 6 events out of 36. And we said there was 1 overlap, so 1 over 36. And I'm going to bring this plus down, and I'm going to bring this minus down. When we're adding or subtracting fractions that have a common denominator or bottom, we can just put everything over that bottom and do the addition and subtraction up top. So these are the same, and it's only because these bottoms all match. They all match, so we can do that 36. So if I add up the top, I've got 5 plus 6 is 11, minus 1 is 10. 10 on top, 36 on bottom, and it matches what we got right here by just counting them. This is an example of how we get the addition rule. And while you're writing that down, I'll start erasing my other sheet. You guys ready for some more? If you need this up longer, let me know. Going. I need to put that black pen away. I keep trying to draw it. Okay, so the general addition rule for probability. They say for two events, E and F, the probability of E, or maybe I'll change color here so it stands out, pops. So it pops. The probability of E or F equals the probability of E plus the probability of F minus the probability of E and F. So this is when an outcome is in both groups, in both events. Like rolling 2 4s. 2 4s was in the event 8, and it was also in the event doubles. This is the general form. Some teachers teach the weaker version first. I think going with the big one first is the better way to do it. This has got more information, but there are scenarios where we don't need this last category. Sometimes that last category is 0. Zero probability. This is when no outcomes are in more than one event. And to put it in the Monopoly terms, this is like if we're looking at rolling a 7 or doubles. There is no combination of the doubles that equals a 7. In fact, all the doubles are even numbers. The sum is even. So there's no way to get an odd number in the sum. I could just as easily have said a 3 or an 11 or a 9 or 5, something like that. There's no way to get an odd number. So when this happens, these events are called disjoint events. And another name for it is mutually exclusive events. I wish they didn't use 2 different ways of saying it, but this is what it means. Are events that have nothing in common. So if E and F are disjoint or mutually exclusive, This equation simplifies down to probability of E or F equals probability of E plus probability of F. I don't really like doing that because if you just stick with the one above, with the minus probability of E and F, if this can be 0, and so if I'm subtracting 0, it doesn't change the outcome. And that equation up there turns into this when probability of E and F equals 0. So there's no need for two equations. Just do the one that has the minus 1 up top. This. So I want to kind of give you an example that shows up maybe like in the homework. You'll care about that, right? If you need this up longer, let me know. Otherwise, I'm going to move it. I can always bring it back. Just holler. So a category in the homework might have something like this. What is the probability? It's always in the form of a sentence. The hardest part of this class is critical reading. You have to read slowly and turn it into the math. What is the probability of drawing? That's what happens when you pick a card from a deck. It's called drawing a card. Drawing a card that is a 4 or a heart. Let's go with king or heart. And that makes it a question mark. So what this is asking in terms of that fancy way we were writing it, the probability that we get a king or a heart. When we have the or, we write them as separate things and put a plus between it. Or turns into addition in probability. Then we got to subtract the event, if there is one, that it is a king and a heart. Maybe I'll do an and symbol. There we go. So if you're unfamiliar with this, you can always go look at a Google image. I want to do that here real quick. Maybe I can. Maybe I can move this to the side a little bit. And I can bring out my Google thing and make it a little bit smaller. Oh, we don't want to go too small. That'll work. I can see that there's, maybe I need to make it a little bit bigger. This is a king, this is a king, this is a king, this is a king. There are 4 kings. So the probability of getting a king is 4 out of 52. The probability of getting a heart, we said there was 13 in each suit, so 13 out of 52. And the probability of getting a king and a heart, if you look closely, this is the king of diamonds, the king of clubs, the king of hearts, the king of spades. This card is a king and a heart. So there's exactly 1 card that meets that criteria. So plugging these into that equation up there, I get the probability of a king is 4 over 52, plus the probability of a heart is 13 over 52, minus the probability that it is a king and a heart, 1 over 52. When the denominators or bottoms are all the same, we can make that the denominator of a big fraction and just do the things that are on the top. 4 plus 13 minus 1. That ends up being 16 over 52. And more than likely, the computer will want a decimal answer. Usually. Every once in a while, it gets a wild hair up its ass and says, I want fractions. So you got to read carefully. That's an example of what you can expect to see on the homework.
This was going over 5.2, correct?
Yeah, this is 5.2.
All right, and we skipped chapter 4.
Yeah, we're going to do chapter 4 later.
Okay.
It's chapter 4 is more on how do we make lines out of this and stuff like that, and it's more applicable to later chapters after the midterm. So I tend to use the information there. I don't want to clutter your brain with crap you don't need for the midterm. If you need that longer, let me know. Otherwise, I'm going to switch. A little bit more in 5.2. It's called complements. Oh, that's my black pen. Get rid of it. When the probability of 2 different events are such that probability of E plus probability of F equals 1. E and F are said to be complements. And the way we could note it is we can say F is the complement of E by putting a C up above. Complement of E. And the same is true vice versa. E is the complement of F. So I could rewrite that equation up there as probability of E plus the probability of the complement of E equals 1. So what this really has is this has the complement of E has all the other outcomes, and I mean all the other outcomes that are not in E. Maybe I should just say all the outcomes that are not in E. In terms of dice or something like that, it could be probability of rolling a 7 and probability that the roll does not equal a 7 is one type of example. We could do a lots. In terms of the deck of cards, we could say the probability that the card is a king or the probability that the card is not equal to a king. And I could replace king with hearts or diamonds or spade, whatever category I want to have. I could be very specific. I could say the card is the king of hearts and the card is not the king of hearts. As long as these two, when added together, events E and F have all the possible outcomes between them. Let me pause for a little bit. There's a lot to write down. Holy shit, that looks like a weird word. I'm gonna rewrite that. It should say hearts. Notice any of these scenarios, there is no overlap between the two groups. E and C are definitely mutually exclusive groups. That doesn't mean all mutually exclusive events are complements. Like rolling a 7 and rolling doubles are mutually exclusive events, but they do not list all the possible combinations of rolling 2 dice. So they are mutually exclusive. So I'll give you a scenario where this is useful. And this is where you will see this shit on the homework. I promise you, there are problems like what I'm about to do on the homework. If you need this up longer, let me know. So you'll get an example like this. Example. There are 18 girls and 12 boys. If 4 kids are chosen, what is the probability at least one is a girl. Okay, so of this option, let's list out the possible events here, or possible outcomes. I could randomly pick no girls. I could pick one girl. I could pick two girls. I could pick three girls. Or I could pick four girls. At least one means one or more. This is at least, all of these are into the at least one event. And we will get into how to calculate something like this on next Tuesday. So we're not going to have the answer yet, but notice I have another possible event. The event is not at least one. So I could put the 0 in this category. And I can tell you the probability of finding 0 is much easier to calculate than 1, 2, 3, or 4. So in how could we use this? Well, I didn't want, if I calculate, this is easier to calculate, but that's not what I want. I want these. So where that comes in is we use that equation I had where the probability of E plus the probability of E complement equals 1. Which means if I subtract the probability of E from both sides, this says the probability of the complement of E is 1 minus the probability of E. Okay, this is an equation that we will use. It's a variant of this one. These two do the same thing. But in this case, I could say E is 0 girls. So the complement of 0 girls is at least 1 girl. Equals 1 minus the probability of 0 girls. That's where that will come out. And 0 girls means we chose 4 boys. Assuming that it's binary groupings. All 18 and 12 people identified in the binary grouping range. About to hit 5.3, it's shorter. But those are some types of examples you'll see in that class on the homework. You will definitely see something like this where they'll give you an at least or an at most, and you want to use this complement rule. Otherwise, you're going to make this really torturous on yourself. You guys ready for 5.3? Almost done.
Yes.
5.3 is on independent events. If we have two or more events, where none of the events affect the outcome of other events, they are independent. And a quick little side blurb. In 5.4, we will do dependent events. So we'll get there. But we're going to start with independent events. An example of this is rolling 2 dice. Ignoring that the dice, when you roll them, they might hit each other. They still don't, it might be affecting what happens, but it doesn't affect the probability. So rolling 2 dice are independent. Even if I get a 1, maybe I should do 6s. A 6 and a 6. If I get 2 6s, these are frequently called boxcars because these look like train wheels. Other fun fact for you, 2 1s are called snake eyes. There's some fun fact on that day. We've already got too much shit going on. Notice that these can result in the same roll. So independent does not mean mutually exclusive. This can occur when we're drawing cards. From a deck. If we put the card back after every draw. You guys ready for the equation? If you need this back up, let me know. I'm just putting it to the side. When events E and F are independent, the probability of E and F equals the probability of E times the probability of F. In the example I just gave, the probability that the first die equals a 6 and the second die equals a 6. That's the same as the probability the first die equals 6 times, and I'm using a dot because we have x's for other things in this class, so the dot means multiply, times the probability that the second is a 6. There are 6 outcomes on each die. Only one of them is a 6. The probability is the same on both dice. It's 1/6. And when you multiply fractions together, you multiply the tops together and you multiply the bottoms together. So 1/6 times 1/6 equals 1 times 1 on top, which is 1, and 6 times 6 on bottom is 36. You'll notice this kind of works for finding the number in the samples. Number of possible outcomes is the bottom. Or the number in the sample space, n of s, in this case is 36. So two big takeaways from today. And I'll do another example, but I want to make sure we hit the takeaways real quick. We had probability of E or F, and that led to addition between them. And then we had the minus probability of E and F happen simultaneously or with the same thing. So or leads to addition. And if you're looking at two different events and you're doing E and F, and they are independent, the and leads to multiplying. This applies to the thing like king and heart. King and heart that we were doing just a little bit ago equals the probability of a king times the probability of a heart. The probability of a king is 1/13. The probability of a heart is 1/4. We multiply those, we get 1/52. So it does apply in the other situations. But just remember, and goes to multiply or goes to add. And we'll do Yahtzee real quick. Has everyone played Yahtzee? This is a common game with dice. If you need that back up, let me know. The game of Yahtzee, just as a reminder, or if you have not played, rolling a Yahtzee is getting 5 dice to show the same value. So like 1, 1, 1, 1, and 1. We can do this with 1s, 2s, 3s, 4s, 5s, or 6s. There are 6 different Yahtzees you can get. Okay, so the probability of getting a Yahtzee on the first try. On first throw. In Yahtzee, you can pick up dice you don't want to use and 2 more times for a total of 3 different tosses. The probability of getting a Yahtzee in the long run like that is a lot more work to calculate. I'm not even going to do it in this class, but 1 throw is easy. So let's pick 6. No, I'm going to pick 4. We'll use a 4. Let's say they're all 4s. So this is the probability that the first equals a 4 and second equals a 4 and third equals a 4 and fourth equals a 4 and fifth equals a 4 and sixth equals a, nope, there's only 5 dice. And fifth equals a 4. I'm getting a little carried away. And these are all ands, and they are all independent events. So I'm going to eliminate the 4. I'm just going to say probability of first times probability of second times probability of third times probability of fourth times probability of fifth. And we'll just pretend I wrote equals 4 on all of these. So this is 1/6, and this is 1/6, and this is 1/6, and this is 1/6, and this is 1/6. One way to write this is 1 over using exponents. When something appears repeatedly in multiplication, we can write it with an exponent. 6 to the 5th power means 6 times 6 times 6 times 6 times 6. So that's the probability of rolling all 4s. But let's just say you wanted any Yahtzee. So any Yahtzee, let's stick with the specific Yahtzee here. So the specific Yahtzee, all 4s here, is 1 over 6 to the 5th power. If you do not have an exponent card in your calculator or button on your calculator, you're better off doing 6 times 6 times 6 times 6 first. finding out what it equals. In this case, 7,776. And then doing that division. 1 divided by 776. And I am getting 0.0001286. If you want any Yahtzee, well, there's 6 different possible Yahtzees. So I could say probability with Yahtzee of 1s, or Yahtzee of 2s, or Yahtzee of 3s, or Yahtzee of 4s, or Yahtzee of 5s, or Yahtzee of 6s. And remember, the ors turned into addition. So this would be probability, without the y's, probability of 1s plus probability of 2s plus probability of 3s plus probability of 4s plus probability of 5s plus probability of 6s. In this case, we're going to add this. I'm going to leave it as the 1 over 6 to the 5th here. We're adding all these up. And if we do that, the common denominator, we can add up all the 1s. We have 6 on top over 6 to the 5th power on bottom. I'm going to write that so it doesn't look like a 65. And one of the 6's on top cancels with one of the 6's on the bottom. And this reduces down to 1 over 6 to the 4th. Almost done. Almost done. Hang in there. Like less than 5 minutes left. If you need this up longer, let me know. You might, because it was a lot to write. Okay. So we said probability of any Yahtzee. I just showed, I'm off screen, was 1 over 6 to the 4th. And we did it by doing the full Yahtzee version. Figuring out there were 6 different Yahtzees, doing all the dice. Another way of doing that calculation, it might help you when you're thinking about stuff, is if we just want any Yahtzee, does the first die matter? First die's outcome matter? Do I care if I roll a 1, a 2, a 3, a 4, a 5, or a 6 on the first die? If I just want any Yahtzee? No. The only thing I care about is that the rest of them match the first. So another way to think about this is the probability that the second matches the first. And second or third matches the first. And fourth equals first. And fifth equals first. The ands turn into multiplication. I'm going to say second times third times fourth times fifth. It doesn't matter what outcome lands on the first die. Let's say it's a 5. The second die has 1 chance out of 6 of getting the same result. It needs to roll the exact same number So this would be 1/6. This would be 1/6. They're all the same. And so when we do these together, this turns into 1/6 to the fourth. And it's a quicker way of doing it than what we did with finding a Yahtzee for a specific one and then calculating any Yahtzee. And that's it. That's today's lecture. That was a full 2 hours, wasn't it? Normally we won't last that long. You guys have any questions? See something in chat? It was a lot, right, Natalie? A lot of it, the over an hour of it was all just text, and we didn't do any like calculations in 5.1 really. Not a whole lot, not anything you hadn't done before. 5.1 we did the equivalent of the same thing as relative frequency, which you guys did in chapter 3 or 2, chapter 2. So 5.1 was a lot. I agree. This was a long night. If you don't have any questions, you're free to go.
Would you say this would be the chapter that's going to be like super heavy on the midterm?
There will be more than one question from this chapter on the midterm, yes. There will be several questions from this chapter on the midterm.
It probably doesn't matter, but roughly around how many questions are there on the midterm?
I want to say I generally do around 20. I will look. Email me.
And then like,
To remind me to look.
Also doesn't matter, but are they like multiple part questions like the homework?
Some of them are, but most of not anything like the homework has where there's 8 parts. That's ridiculous.
Yeah.
The midterm
Okay.
is in math lab. But I tend to pick the
Yeah.
problems that have less steps. The final will not be in math lab. The final will be on Canvas. I will give you on the final. I will give you all the calculations from StatCrunch. Your job is just to tell me what the statistics mean. So when we get there, but the midterm is still on my math lab. And I'll look up how many. I wonder if I can check now. Let me stop sharing so you can't see what I'm
Thank
doing.
you.
I'll be sneaky about it. And I have to click on assignments and I have to do manage view so I don't see it from a student's view because you can't see it yet. The midterm review is actually already available, so you can see the review already. Let me see if they have the same number of questions. So the review has 36 questions, and the actual midterm only has 28. And I'm not gonna, they are similar. And I'm not gonna tell you which 28. But you should have access. Let me switch to student view, and I can share screen now. Let me go back to sharing screen. Zoom, where are you? Share screen. So if I scroll down, you can see the midterm right here. You will have 2.5 hours to do it. So you'll have a lot of time. There's 36 questions here. There's 28 in the actual test.
Okay. Thank
Okay.
you.
Okay.
Have a good night.
You too. Anybody else?
I know this might sound like a funny question too, but when you record videos, where do you put them? Because the videos that are on my math lab, they're like
Those are the
older
old
videos.
ones. Go to, I'll show you that too. Let me share screen again. I don't think I'm sharing. Yeah, the one I have 3 different stats classes, changing the links every time because I have links for people that work ahead. So I have to have the videos in the math lab that are older. So if you go to YouTube, maybe I should just go to regular YouTube where you can't see my channel by default. You're going to search for Professor Hefe. And you'll see my face. There I am. That's me with my NASA background. It usually shows what the latest ones I've done are. That is not me, so maybe just clicking on my face. And you want to go to playlists. Playlist, you will see Math 21 Stats Fall 2022. And they are all in here. It takes a while because it's a 2-hour video. It takes a while for this to convert to YouTube and upload it. So it won't be ready tonight. I will set it to hopefully Goa. I'll have it translating it or going up tonight. If not, I'll do it tomorrow morning. But that's where you'll find them. So Professor Hefe on YouTube.
Thank you.
Uh-huh. Anybody else? All right. Have a good day.
I have a question. Sorry.
Yeah, what's up?
Sorry, that was last minute. I have a question with the homework.
Okay.
For chapter 3. There's one of them. Can I share my screen with you?
Yep.
Let me see. I was shopping earlier.
Shopping? Shopping for what?
For a date. Gotta get me some new t-shirts.
Nice.
Nah, but the bell curve stuff kind of like throws me off, if I'm being honest. Like, you know how I said last time, like whenever I saw it, I was like, what the, like, it just looks like gibberish to me.
Mm-hmm.
Like, it just all looks like, it's chapter 3, right?
Yeah.
Let me see. Chapter 3, oh, come on.
You weren't actually here at the beginning with when I was doing this with Caprice earlier. I bet
Oh,
she
you
asked
were?
the same damn thing as you. And I
Let me
don't think I had clicked record yet.
I'm
But let's see what you got.
trying to think which one it was. I mean, honestly, like,
Well, start
from
sharing
here
screen.
on.
I can help you. Like I can show you ways to find it quicker.
Oh, okay. It's not sharing it?
No.
Oh, what the? Okay, can you see it now?
It's loading. Yeah, there we go.
Okay.
Okay, so notice on the left, if it's got like question 14's got a red X with a green check mark, it means you've missed part of the problem.
Yeah.
So if you're looking for something where you miss something, check for the ones with red X's. Those will be the
Okay.
ones that you struggle with, and you can show me those, and we can go with those.
Okay. So, but this one right here was like it was it was
Okay.
chose the wrong one.
15 might be. You might have been stuck on that one.
Yeah.
Yep, this is exactly what she asked me. So
Okay.
I'm gonna write those values down, and then I'm gonna take the screen back, but I need to write them down first, so don't close that yet.
Okay.
So we got mean of 100, standard deviation of 11, and then we've got 78 to 122 is A. B is less than 78 or greater than 122. And C is greater than 122. All right, I'm going to steal the camera here.
All right.
Okay, so we're going to draw our bell curve.
Okay.
You should do this when you have these problems. What you're going to put in the middle is the mean, the 100.
Okay.
Then you're going to make 3 hash marks to the right and 3 hash marks to the left.
Okay.
And what you're going to do is just add that standard deviation each time as you go to the right. So it's 11. I'm going to add 11 as I go to the next hashtag. 100 plus 11 is 111.
Yeah.
111 plus 11 is 122. And do it again is 133. Going forward is a little bit easier than subtracting. Subtracting is 89, 78, and 67. If you do it in a calculator, you'll see those.
Okay.
Okay, then what you're going to do is you're going to like make little divider signs here. And assuming you've been taking notes, you will be able to find in your notes that anything in this area or this area is 34%.
34%. Yeah.
We got 13.5 here, here, 2.35 here and here, and 0.15 there, and 0.15 there. Okay, notice between, this is 1 deviation up, plus 1 deviation. This is minus 1. So within 1 deviation either way, 34 plus 34 is 68%. If I go within 2 deviations or outward from the mean 2, and I add up that, and that, I'm going to get 95%. And if I go out 3, I'm going to get 99.7%. Those can help speed you up depending on what they ask you.
Okay.
So once you have that written down, we'll look at what they asked you because I got it written above.
Okay.
Ready?
Yeah. Okay. I got it.
Okay. So they want from 78 to 122. Where do I have that on my range? 78 is right here. 122 is right here. That's conveniently lines up with this. So it's
Yeah.
2 deviations. The answer there is 95%. So that's the answer to A.
Okay.
Okay, when they ask you for the other one, less than 78 or greater than 122, less than 78 is everything in this direction, and less than one or greater than 122 is everything in that direction.
Okay.
So you have 2 options. You can add up the 0.15, the 2.35, the 2.35, and the 0.15. Or we can actually use that complement rule we were just talking about today. If I know this middle section is 95%, and the whole thing adds up to 100, B should be 100% minus the 95%, which is 5%.
It's 5%. Okay.
That's the complement idea.
Yeah.
You'll notice if you add these values, 0.15 to 2.35 is 2.5, like $2.50.
Yeah.
And we got 250 on both sides, that's 5. So you get 5 either way, but it is the complement idea. And then I think they asked you about greater than 122. You're just looking at this side right here. So that's 2.5. So that's how you have to do it. And I recommend like doing a similar question after you enter it in. Do a similar question. You'll get different numbers. And try to do this idea without me showing it to you. See how you do. But I think you can do it. What it takes is remembering these values right here.
Yeah. Okay.
Okay?
Yeah, for me, it's just like the wording. Like whenever you do it, it like makes sense. And
The
then
whole
like I see
class is
like,
going to be like that. This is entire
yeah,
class. It's a word problem class. Believe it or
yeah,
not, the math isn't actually all that hard.
yeah. The
It,
math's not hard. It's the wording that really like tricks me up because it's
right,
like when do I use each certain thing, you know?
right, and that just comes
So
with practice.
yeah. All right. Well, thank you.
Happy I could help.
Have a good one.
All right. Good night. Talk to you later.
Good night.
Recording stop.